Hello everyone, this is Zhimao Fan. I want to present the proposed paper, Have Wavelet Attention on Mnet Plus for Low-Light Image Enhancement. I'm a graduate student from the Department of Electrical Engineering at National Zhongxin University, Taiwan. This is our outline. We are first going to the introduction and introduce some related works in our proposed model. Then we will explain the proposed architecture and discuss the experiments, include some visual results. Finally, I will conclude our work in the end. First is introduction. Low-light image enhancements belongs to an ill-posed problem, which enhance the dark image to inappropriate brightness. We can also see image enhancement as a mapping problem, like mapping the input dark image in X domain to enhance images in Y domain. So far, image enhancement still plays an important role at the preprocess of high-level vision tests, like object detection to improve the visual quality. The main contributions of this paper can be summarized as the following. First, we propose the improved hierarchical backbone architecture Mnet Plus for the test of low-light image enhancement. Second, we propose the efficient feature extraction block called Have Wavelet Attention Block HWAB, which can gain more diversity features in another domain. Third, we experiment on two data sets to demonstrate that our proposed model achieves the state-of-the-art performance in low-light image enhancement in terms of quantitative scores and visual results, even with less computational complexity. Next, we will illustrate our related work. The following figure is the hierarchical model architecture Mnet, presented in 2017 for medical image segmentation. They improved by UNet by using two additional gap path feature paths on encoder and decoder to enhance the segmentation performance. Next related work is about a wavelet transformation. Generally, wavelet transformation has the advantage, which is comprising the time domain and frequency domain details of images or signal, instead of only acquiring the frequency information as Fourier transform. In our experiments, we select the simplest wavelet, that is, harm wavelet, to increase the information from another domain. After the one-order harm wavelet transform, the image will decompose to several subbands, including LL, HL, LH, and HH as following. Then we are going to introduce our proposed method for image enhancement. The whole framework of proposed HWMnet is shown in here. There are three important components in our HWMnet. First, we propose the Have Wavelet Attention blocks, so-called HWAB, to extract additional information by the wavelet transform operation with low computational complexity. Second ingredient is the resizing module in main UNet feature path and gap path feature path. The last one is our improved hierarchical model Mnet Plus, comparing with traditional Mnet mentioned in related work. The architecture of our Have Wavelet Attention block is displayed in here. The DAU means the dual attention unit, which is existing extraction block using the channel attention and spatial attention to extract features and fuse them together to gain more enriched contextual information. In the beginning of the HWAB, the input features are first divided into two parts, F identity and FT, along the input channel. The main purpose of dividing the input features is to decrease the computational complexity and reserve the context information, where F identity is to keep the normal domain features, which can be referred to the paper half-instant network. The other part of feature FT is ready to do the discrete wavelet transformation DWT to obtain the wavelet domain feature FW. Then FW will pass to the dual attention unit to get the weighted wavelet feature FW hat. And we perform the inverse wavelet transformation IWT to reshape FW hat to the shape of FT and become the weighted normal domain feature FT hat. Finally, adding the shortcut features through one-time-one convolution to the residual feature FR, we get the output feature FOut, which has the wavelet attention information. As the resizing module, we use pixel unshuffled as downsampling method and pixel shuffle as upsampling approach in UNet feature path, like this. Here is the difference between conventional MNet model and our improved backbone MNet Plus. In main UNet feature path, we substitute the simple extraction block, which is several convolution layers with activation function and batch normalization to our proposed half wavelet attention block HWAB. Furthermore, using pixel unshuffle as our resizing module to replace the max pooling downsampling. For the gap path feature path in encoder, we add additional shallow feature extraction, where the traditional MNet only extract shallow feature in shallowest layer. As to the gap path feature path in decoder, we use selective kernel feature fusion SKFF to substitute the directly concatenating the output features from decoder. Finally, our HWMnet is an end-to-end trainable enhancement model, and we use Charbonnier laws like this formula to optimize our network. Let's go to the experiment section. We train two image enhancement models separately by LOL dataset and MIT Adobe 5K, respectively. The images in LOL dataset are darker than MIT Adobe 5K, so some of researchers regard the image enhancement model trained on MIT 5K as image retouching task. We use randomly horizontal and vertical flips as data augmentation. For the low-light image enhancement model trained on LOL dataset, our HWMnet achieved the runner-up scores, including the PSNR, SSIM, and LP-IPS. Note that the LP-IPS matrix is the lower the better. We further build the tabular in terms of quantitative scores and model complexity for the top 3 enhancement models in previous table. We can notice that the state-of-the-art low-light enhancement model LL-Flow, which is the oral paper on AAAI 2022, although it has the outstanding performance on enhancing the low-light images, when testing on a 400x592 color image, the flow point operations value is higher than our HWMnet, and the unit is trillion. We think it is attributed to the design of HWAB, where half of the features passing through the attention can decrease the computational complexity, and the design of Wavelet attention could gain more semantic information and details in the training process to keep satisfactory results. Here are the results for the model trained on MIT Adobe 5K dataset, which can be also regarded as image retouching task. Our HWMnet get the state-of-the-art results on both PSNR and SSIM2. This is the visual results on LOL dataset. You can see that our HWMnet achieves the state-of-the-art PSNR, SSIM, and LPIPS scores on single LOL image. For the image retouching, which trained on MIT Adobe 5K dataset, the visual comparisons are shown below. The quantitative scores are still the best among the existing enhancement models. Finally, the conclusion. In this paper, we propose the improved hierarchical backbone architecture MNet Plus for low-light image enhancement, called HWMnet. Second, we propose the feature extraction block, called Half-Wavelet Attention Block HWAB, focusing on the features of wavelet domain, which can enrich the semantic information. Finally, our proposed model achieves the state-of-the-art performance on low-light image enhancements with less computational complexity. Thank you for attending my presentation. This is Zhi Mao Fan, and have a good day.